Hello. Today we are going to learn how to compute volumes by using integration. The topic of this lecture is volumes by revolution. Actually, volumes by revolution topic has two subtopics. The first subtopic is disk method. The other subtopic is washer method. Today we're going to cover the first subsection, which is the disk method. Okay, so let's move to the motivation. First of all, I will give you the motivation. In this motivation, I'm going to explain you how to compute volume by using the general method. All right. First of all, I draw a small schematic here, a plot. Let's consider this is your y-axis. This is your y-axis, and that is your x-axis, and let's say this is your maybe c-axis. Let's consider this volume. All right, so this is the volume that I consider. You know how to compute this volume by using integration, and that we learned in a previous section. Let's consider this is a cross section of this object. Let's say this is a of x. All right. Let a of x is a cross section let's say there's a cross-sectional area perpendicular to the x-axis. Then if somebody has to compute the area by using this cross section, you can simply write it. then the volume is actually integration of this cross section from the start of the region with respect to the x-axis, which is A, the end is B. It's the integration from A to B of this cross section. All right. So this is also explaining Riemann sum. Since you are familiar with Riemann sum, this is also same to Riemann sum. So this is the motivation. This is how you compute the area. And similarly, you can think of some other areas. In this case, this cross section is perpendicular to the x-axis. All right. This is perpendicular to the x-axis. Similarly, you could consider another two cases. The next case is what happened this cross-sectional area is perpendicular to the y-axis. That means this is the case. Y is that, x is that, c is that. So the area looks like this. All right. So in this case, this is the corresponding cross section. And let me write down the formula for this case. Similarly, for the first case, if A of y perpendicular to y-axis, then let's say this point is P and that is Q. This is integration from P to Q, A of y dy. And in the next case, what happened if this cross section is perpendicular to the C axis? Second case, if AC, in this case we consider AC is too big. This is y, this is x, this is c, and this is the corresponding cross section which is A of C if AC is perpendicular. I forgot to put is here. Then the corresponding volume is, let's say this is C and that is D. From C to D, A of C, D, C. Okay, so these are the three cases that we can think of. So this is the motivation. You know this part because we have done Riemann sum early. Now we move to today's class. Today's class is a little bit advanced than what we have learned right now. Now we consider a case like, give me a second. Now we consider a case like, let's say you are given a curve. Okay, let's say you are given a curve like this. This is a curve given to you. And then you know how to compute the area below this curve. That area. Alright, you compute that area and then you rotate this curve about the x-axis. Let's say you rotate this about the x-axis. Okay, that will generate a volume. So the volume should look like this. So you have that part and then you have something like that. So since you have rotated it, so you have this volume. Okay, so this is the volume that you have right now. So it is simple. Let me repeat it again. What you have here, you have a curve like that, and then you can compute the area under the curve, that is that, and then you rotate this area above the x-axis. That will generate this volume. All right, so this volume is generated by rotation. Okay, that's why we have the title as volumes by revolution. That means you rotate it. Okay, volumes by revolution. The method that we're going to learn is the disk method. Let's see how this word disk come. Disk method means if you make a cross section of this object, actually that is a disk. All right, so this is a disk. Okay, like here, these are also disk. This was a disk, that was a disk, and this was a disk. That's why we call this is the disk method. So you make a disk and then you just compute the area of the disk and then you just integrate that. All right, so go back. So I'm taking this everything out and then I'm going to write down the note. Okay. The volume by revolution. This is the disk method. First I write down the note and then I will explain that. The volume of a solid of revolution we are talking about the disk method is that volume is written as V equals pi A to B R of x square dx. If the axis of rotation is the x-axis. Okay, then the next case, V equals pi C to D Ry square dy if the axis of the rotation is the y-axis. Let me explain this little bit. So you have these axes. Give me a second. All right. You have this axis. This is, let's say this is y, and let's say that is x. You have that curve from A to B. Let's say you rotate this one about the x-axis, and then what you get is something like this. This is the same y-axis, that is the x-axis, that is A, this is B, once you rotate this one about the x-axis, what you get is something like this. Okay, now let's get a cross section. Now let's consider this is the radius of that disk, which is r of x. Here you have that point is x, this radius is r of x, you can see that. And then the volume of this disk is, it is so obvious that the volume of the disk is actually pi radius square. Okay, pi times radius square. The radius is r of x and the square of that. All right. That is the volume of the disk. And what you have done here is you simply I'm sorry, not the volume of the disk, it's my bad, it is the area of the disk. Disks are not having volumes, disks are having only areas. The area of the disk is that. Then it is simply the integration, the volume should be integration of this function, which is pi r x square. Here it is from a to b. All right, then you can write this as, you can take pi out because it's a constant, and a to b r x square dx. All right, so that's clear now. So this is what is given right here. So this is the same formula given, I'm sorry, this is the same formula given right there. So this is kind of the derivation. All right, this is kind of the derivation of the formula. All right, cool. Now we just go to the next case. In the next case, we have this volume in other way around. It is with respect to the y-axis. That is, you have something like this. Let's say this is your y-axis, and let's say that is x-axis, and you have this curve, then this is C, that is D. You know how to compute the area of that. Right now you rotate that area about the y-axis and get this shape. The shape that you get should be like this. Give me a second, let me get this little down. Alright, so that's the corresponding volume, and then you can compute the area of that. That's a disk actually. Let's say this point is y, and let's say that is the radius with radius as a function of y, which is ry, and then area of this disk should be, let me copy the same thing over there. In this case, area of the disk should be pi times r y square, and the volume should be integration from c to d r y square dy. All right, so you know the two formulas, how they are formed, and this is the derivation of those two formulas. Now we move to examples. We are going to discuss two examples in this section. Example number 1. Find the volume of the solid obtained by rotating the region y equals square root of x and x equals 0 and x equals 1 about the x-axis. All right, let's draw the region first. I take this to be my y-axis, and I take this to be my x-axis. First draw that y equals square root of x. Okay, y equals square root of x. The shape of that should be like this, concave down. Alright, then x equals 0. X equals 0 is that line, and then x equals 1, which is this line. Alright, so the area should be, give me a second. Actually, I made a small mistake here. This should be y equals 0. Put it as y equals 0. Y equals 0 means y equals 0 means that. Okay, y equals 0 is that. This is x equals 1, and that is y equals square root of x. Alright, so this is the corresponding area. We rotate that about the x-axis. We rotate this about the x-axis, and then what you get is something like this. Alright, what you get is something like this. It's called a paraboloid. It's a solid parabola. It's a parabola, but it's a solid thing. It's called a paraboloid. So this is the shape that you have. Now we make a cross section. This is the cross section. Alright, now we need the radius, which is right here. Let's say that is x, and then this is the radius, r of x. Okay, now you have to find the radius as a function of r. This means the radius as a function of x is radius as a function of x. You know that this curve is y equals square root of x. Actually, the radius is height of this. Okay, the radius is actually this height. Give me a second. It is this height. All right, that's that height. So that is actually square root of x. Thus, r of x equals square root of x. All right, so you know the radius. Now it is very simple. You just have to plug this rx into the formula. This is the formula that you have. This is the formula. You have to plug that into that formula. Then your v equals pi times integration r of x square dx. Here it is 1, here it is 0. The integration from 0 to 1. Okay, you have to plug rx square. So this should be pi 0 to 1 x dx. This equals pi times x square over 2. 0 to 1. And this equals pi over 2. You apply the upper limit, which is 1 minus 0. So the answer is pi over 2. So this is the corresponding volume. Okay, that is the volume of this paraboloid, which is very easy. The only trickiest thing that you have to compute is the radius rx. Okay, you have to compute this radius. Once you have this radius, everything is so simple. All right. All right, go forward, and then let's move to the example number 2. Find the volume the solid obtained by rotating the region bounded by y equals x to the power 3, y equals 8, and x equals 0 above the y-axis. Alright, let me draw the shape of this case. Now this is y, that is x. The first function is y equals x to the power 3. So the shape should be like that. Then next is y equals 8. Let's say 8 is right here. So this is y equals 8. That is y equals x to the power 3. And the next case is x equals 0. That is that. This is x equals 0. So you take that area and then you rotate that about the y-axis. Okay, you rotate like that about the y-axis, and that also makes a paraboloid, like we discussed earlier. That's also a paraboloid, but the thing is the shape is different. In previous case, this paraboloid was symmetric about the x-axis. All right, but this give me a second. But this paraboloid is symmetric about the y-axis. That is x. This is y. Again, you make a cross section. This is number 8. You make a cross section like this. This means radius as a function of y. All right, then you have to compute what that radius is. That should be a function of y. Keep your eye on that. This should be a function of y. Okay, you know that the radius can be given by this length, that length, which is actually this function value. Okay, the value of that function. Okay, that function is actually that function is y equals x to the power 3. This function is, let me write it a little below. That function is y equals x to the power 3. Now this should be a function of y. Alright, then what you do is you just solve this for x, solve this equation for x, then you get y 1/3 equals x. Okay, y 1/3 equals, that means you can just bring this 3 into y as a power of 1/3. Alright, then y 1/3 equals x. And then radius, this should be y to the power 1/3. Since you know the radius, everything is so easy. Now you have to plug that into the equation. V equals pi integration from c to d y square dy. Okay, this is pi, c should be 0, d should be 8, 0 to 8, and then ry should be y to the power 1/3 dy. So this should be pi y to the power 1/3. That is the power rule for integration. If you can remember the power rule for integration, it should be like this: y to the power n. It's integration. It is integration y to the power n. If you have something like n power, this is actually y n plus 1 over n plus 1. Alright, so you write this to be y 1/3 plus 1, 1/3 plus 1, then you apply the limits from 0 to 8. Okay, here you have 1/3. There you had n. If you had n, then it's n minus n plus 1. If you had 1/3, then it's 1/3 plus 1. Right, now just simplify that. Pi y to the power 4 over 3, 4 over 3, 0 to 8. Then you write this to be 3 pi over 4. And then y is 8 here. 8 to the power 4 over 3 minus 0. Alright. Give me a second. I made a small mistake here. Actually, this should be ry square. I just dropped the square. It's my bad. So this should be raised to the power 2. Okay, because this 2 is right here. I forgot that. I'm sorry about that. Then this is to be raised to power 2. And then let me write that. Let me delete everything from here. And then this should be pi 0 to 8 y to the power 2 over 3 dy. Simplification of that part goes like this. It is y 1/3 to the power 2. Then you can just multiply the powers. That means you can multiply 1/3 by 2. Okay, you have learned this in calc. You have learned that one in calc 1, where you learn indexes. Alright, then this should be pi y 2 over 3 plus 1, 2 over 3 plus 1, and then you have to apply the limit 0 to 8. and then this is pi y 2 over 3 plus 1 should be 2 over 3 plus 3 over 3, which is 5 over 3. Alright, so this is y to the power 5 over 3 here. 5 over 3 from 0 to 8. Then you write this to be 3 pi over 5, 8 to the power 5 over 3 minus 0. And then you write 3 pi over 5 and then 8, 5 over 3. Okay, then let's check whether you can simplify this part further. Give me a second, I had to do that and bring that here, and then how to simplify this. Simplifying this is taught in Calc 1. You might remember that, right? You can write 8 as, you can write this 8 as 2 to the power 3. Okay, 8 is 2 to the power 3. And then you just write this, the power 5 over 3. Alright? Because 8 is 2 to the power 3. And then this is a power of a power. Here, power of a power. If you have something like power of a power, you can multiply the powers. So you can write this to be 2, 3 multiplied by 5 over 3. Okay, then you can cancel that 3 with that 3. And then this should be 2 to the power 5, which is, let me write it down. What is 2 to the power 5? 2 times 2 times 2 times 2 times 2. Alright, which is 2 times 2 is 4, 8, 16, 32. Okay, this is 32. And you write this as 3 pi over 5 multiplied by 32. 32 times 3 is 96 pi over 5. Alright, so this is the final answer here. Alright, we discussed two problems. This is the second problem. Let's come from the beginning. This is the topic, the volumes by revolution. There are two methods. Those we learn in two classes. And the first method is the disk method. Then we learn washer method in the other class. Today we're going to learn disk method, how to use the disk method to compute a volume. Alright, so I gave you motivation which explains a general method of computing volumes, and thereafter I gave you the formula. There are two formulas you could use. So this is the first formula. It addresses when your area is perpendicular to the x-axis, and this is the next case. This case suitable when your area is perpendicular to the y-axis. We discussed one problem. That is the case where the area is the cross-sectional area is perpendicular to the x-axis, and then we move to the next case where the cross-section is perpendicular to the y-axis. So that's end of the section, and then we can learn about the next method in the next class. Thank you very much.